Alright, this is a variation of a pretty standard physics problem. You see this problem a lot. Sometimes you see it with charges and you're looking for electric fields or forces. In this case we have currents and we're looking for a magnetic field. So here's the setup. We have two currents situated at two vertices of an equilateral triangle. So we have current 1, which I've called I1 here. We have current I2. The I1 current is coming out of the page. The I2 current is going into the page. The triangle has a side D, so there's a distance D between the currents. And there are also distances D here and here away from the third vertex, at which we are looking for the magnetic field. We want to know what the field is at the third vertex of the triangle due to the current I2 and I1. So each of those currents is going to produce a magnetic field. Therefore, the total field at that point is going to be the vector sum of the fields B1 arising from I1 and B2 arising from I2. So how do we get those? Well, I've drawn down here a circle around I1 and a circle around I2. We know that the magnetic field is going to make circles around the currents. The direction of those is going to be given by the right-hand rule. So for I1, the right-hand rule for fields is I take my thumb and I point it in the direction of what's straight. My fingers then will tell me what's curved. So in this case, the current's coming out of the page into the phone. You should think of it like that, which means my fingers are going to tell me the direction of the field. In this case, the orientation is counterclockwise. Using the right-hand rule for I2, my thumb is going to be going, if you can see this, into the page. So move this over, which means my fingers are going to tell me the direction of the field. In this case, it's going to be oriented clockwise. So I've got a counterclockwise field here, a clockwise field here. So for the field lines, which are what I've drawn, the actual field at any point is going to be given by a line, or a vector I should say, that's tangent to these circles. Right? So that's what I've given here. I've given the field at the point where the side of the triangle intersects the field line, the circular field line here. It's going to be tangent to the circle. So here I've drawn a tangent line at this point, and because it's a tangent line, and because the side of the triangle passes through this point, remember this point is at the center of the circle. Because this line passes through the center of the circle, that means this line is directed along a radius. Because this field is tangent at that point, the field and this side of the triangle have to be perpendicular, just because radii are perpendicular to tangent lines through which they pass. Same thing over here. So it's got to be perpendicular to the side of the triangle. So what I'm going to do now is extend that logic up to the vertex. There's another larger circle that passes through this point here from I1 and another circle that passes through this point from I2. Those two circles are too big for me to draw. It's just going to make everything convoluted anyway. So I'm just going to take the same logic I did, have the field line here, and extend that up and say, okay, what would it look like for the circle passing through this point? And I get something that looks like this, which I've called B1. Over here I get something like in red, which I've called B2. So B1 is the field arising from I1. B2 is the field arising from I2. And what I've given you on the right here are the magnitudes of those fields. Right here, let's get the phone over. The magnitude of B1, this is just the formula for the field due to a long straight current carrying wire. Mu naught I1 over 2 pi d. D is the distance between the source current and the observation point. B2 is mu naught I2 over 2 pi d. Okay? Now I need to sum them up vectorially. So to do that, let's run through the geometry. What I've drawn here is the bisector of this vertex. I want to draw that because it's a vertical line and it's going to serve as my y-axis. I'm going to impose Cartesian symmetry here. So this bisector gives me the y-axis. Of course, if I'm bisecting an angle in an equilateral triangle, That angle is 60 degrees. Bisecting it gives me two angles of 30 degrees. I've also drawn the horizontal line here, so the geometry here should be in green. The horizontal and vertical lines are just showing you how the geometry works. The horizontal line is going to serve as my x-axis. So I know that this green dotted line and this green dotted line are perpendicular, right? They have to make a 90-degree angle. Therefore, if this portion of that angle is 30 degrees, this portion has to be 60 degrees. Same thing over here. If this portion is 30 degrees, this portion has to be 60 degrees. I've got to add together to give me 90 degrees. I can do the same logic here. We've already decided that the red vector B2 is perpendicular to the side of the triangle. The blue vector B1 is perpendicular to this side of the triangle. So if this much of that angle is 60 degrees, 30 degrees has to be here. 60 degrees here, 30 degrees have to be here. So I'm exploiting these right angles to give me the angles that I need. Once I have those angles, I proceed in the normal fashion of just taking these vectors, resolving them into components, and adding them together. So here's what I have done here. In the x direction, I've got negative b1 cosine 30 degrees, that's the component here, plus b2 cosine 30 degrees, that's the component here. That will give me my the x component of my total field, which I've called bx. by, I'm going to do the same thing. b1 sine of 30 degrees, that's the component here, plus b2 sine of 30 degrees, that's the component here. Notice I'm getting my negative sign here by inspection. I'm calling to the right positive, so I can see that that vector has to go in the negative direction in the on the x-axis. Similarly, in the y direction, I've got two components that are going up. I'm going to call that positive. I just reminded you and myself what the sine of 30 degrees and the cosine of 30 degrees are. Sine of 30 degrees is 1/2. Cosine of 30 degrees is √3/2. That's going to come in handy in just a second. Now that I have my components, I just proceed to add them up in the x direction. If I factor out the cosine 30 degrees, I get this expression. I'm then going to substitute in for cosine of 30 degrees and substitute in what I have from up here for the actual fields, do some factoring, and what I get is this expression here. √3 mu naught over 4 pi d, quantity I2 minus I1. Same thing in the y direction. I'm going to factor out the sine of 30, substitute in the values for b1 and b2, and what I get is mu naught over 4 pi d, quantity I1 plus I2. Now, if you have numbers in a problem that you're working, now I think would be a good time to substitute in for the currents. It will simplify things greatly. We don't have numbers here. I'm going to solve it symbolically. So I'm going to take it farther symbolically, but if you have numbers, it would be a good idea to simplify this here in terms of the numbers that you have. Okay, so once we have the components, this is all very standard. I'm going to use the Pythagorean theorem to put them together. Here, this is the magnitude then of the total magnetic field. You can run through the algebra here yourself. The next step, I'm just factoring out, taking mu naught over 4 pi d, taking a square root of that quantity and getting it outside the radical. Once I can proceed there. Here I'm just working with the quantity under the radical. I'm foiling out I2 minus I1 quantity squared and I1 plus I2 quantity squared. Doing some algebra down here, factoring out whatever else I can. What I come up with is 4 times this quantity, I1 squared plus I2 squared minus I2 I1. To take a square root of 4, that's going to give me 2, which I have pulled out of the radical. And remember what I had over here was mu naught over 4 pi d. If I factor out a 2, or not factor, if I bring a 2 out from under the radical, that's going to cancel one of these 2's. Gets me magnetic field magnitude there. The angle, inverse tangent of the y component over the x component. You can see what I've done here. This actually simplifies pretty well. I've got √3 times mu naught over 4 pi d in the numerator, mu naught over 4 pi d in the denominator. The mu naught over 4 pi d is going to cancel out, and I'm left with this relatively simple expression, root 3 times I2 minus I1 over I1 plus I2.